been asked to take care of the talk today. I don't know. I don't see neither William nor Ferenc.
I'm here.
There is William. Okay, all right. Spoke too quickly. So it's a pleasure. It's a real pleasure to have Wolter, especially in the circumstances that I was describing. So Wolter is, you know, a member of this illustrious Dutch school in representation theory, special functions, and their applications in mathematical physics. And so I'm really, well, I was hoping that Wolter, and I still hope that he will visit as soon as possible. He was due to be at the CRM for an extended period, but for lack of being able to do that at present time, we'll have him virtually. So without further ado, Wolter, please.
Yes, thank you very much, Luc, and thanks for the invitation to give this talk. So yes, I will talk about, well, try to talk about duality functions for interactive particle processes and orthogonal polynomials. So this is a joint work with Gioia Carinci and Chiara Franceschini and Cristian Giardinà and Redig. And these are people from probability. So they work a lot on these interactive particle processes. And at some point they found a link with orthogonal polynomials, and that was basically where I came in. Well, let's see if it works. I now have a problem. Yes, it seems to work. So here's what I will try to talk about a bit. So I will start by saying something about stochastic duality. So what it is. And then, well, because at some point these orthogonal polynomials came in as duality functions, I will try to explain some methods to find these orthogonal polynomials and I'll describe orthogonality in terms of these duality functions. So we have two methods here. There were more actually, but well, we cannot talk about everything here. So we have a scalar product method and one using symmetries. And so this is, and then the last part's more about recent work where we try to use this for asymmetric particle systems. So basically, the whole setup was done for symmetric particle systems, and then we try to extend that also to the asymmetric case. Okay, so so let's try.
Do you mean things like
stochastic duality
exclusion process?
I'm sorry?
Are you dealing with exclusion processes?
Yes, so I will basically talk about inclusion processes and exclusion processes. So I will introduce them in a minute. So first some, well, this is kind of general setup, but it's basically for this inclusion and exclusion processes. So here's the definition of stochastic duality. So we have two Markov processes, xi, both on the state space omega I. And we say that if we have two of those processes, they are in duality. If we have a function d, which is so defined here on the Cartesian product of the two state spaces, and in such a way that if we take the expectation with respect to the first variable of this function, then that should be equal to the expectation with respect to the second variable. So that's the definition of duality. And if the two processes are the same, we say that the process itself is self-dual. And today I will basically only talk about self-dual processes. So people use this in these interacting particle systems to try to say, well, to try to look at some difficult process and try to relate it to a simpler process. And if you can study that one, you hope to be able to transfer some properties back to the more difficult process. And if you have, well, so for a self-dual process, that seems, well, not so useful, but actually what they do there is you have some interacting particle process. And if you want to study the process with many particles, you can hopefully relate it to the same process, but then with only 1 or 2 particles or so. So that's where this duality is used. So this is the definition, but what's actually more useful, at least for me, was this one. So this is a property or another characterization of duality. So if we look at the generator for this process, so we look at the infinitesimal generator for the 2 processes, then you can act with this generator on the duality functions, on functions, of course. And then this duality property is the same as saying that if you act with, well, first generator L1 on the first variable of your duality function, that's the same as acting with the L2 on the second variable. So in case of self-duality, L1 and L2 are, of course, the same. And so
may I ask a silly question, please?
Yeah, sure.
It seems to me this D, I mean, it's not, that doesn't seem to define it uniquely. There could be many such Ds.
There can be many, yes.
And also, what about just the trivial D where everything maps to 1? Doesn't that satisfy?
That's a good question. I actually don't know.
The average one.
Maybe it satisfies the definition, but it seems not to be useful.
But that means it always exists. 1 always exists, so they're always dual.
Yeah, that's a very good question. I actually don't know. So I think I've never seen this. So I think that, let's see, if you take the function 1.
Well, of course, these might be infinite, but let's say it's a finite space.
Yes. Okay, maybe there should be an extra condition that your function should not be constant or something.
I would think so, because it doesn't really characterize pairs of processes, since that it always exists.
Well, maybe we'll see from the example. Maybe there is an example. Then
yeah, there will
see what it's
be examples, but
yeah.
Yeah, I actually never thought about this, so I will just move on and see what happens. Maybe in the examples it will be more clear what. Maybe there should be an extra property. I've never seen it with this extra property, but it seems to be okay that if you take D as a constant function, then yeah, it's of course always the same. Okay, so here's well, one of the examples. So this is called the symmetric exclusion process. So what you have as a state space, you have just a set 0, 1 up to 2k. K is a half integer here. And you have n of these, so you take this to the power n. So basically you have n sides here. And on each side you can have at most 2k particles. So this whole thing here is 2k basically. And so xi, here's the number of particles on side I, and what happens is that particles can jump from side I to side j with a certain rate. So you can take a particle and move it to side j at a certain rate. So here are the rates. And so this is symmetric because, well, the rate for particles jumping from side I to j is the same as the rate from particles jumping from side j to I. Okay, so this is the symmetric exclusion process. So you can have only finitely many particles on each side, and of course the number of particles stays the same all the time. So that's conserved. And then there's this other process which is very closely related. This is the symmetric inclusion process. It's almost the same, only now you don't say that there can be at most 2k particles on each side, but there can be arbitrary number of particles. So the state space here is just the natural numbers, including 0 here to the n. And the same happens here. Particles can move from site I to j, and it's all at the same rate. And the rates are almost the same that we had before. So these are the rates here. Only if you replace k by minus k, you get the previous one, basically. So you can, what basically happens is that you can study these two processes basically at the same time. So I will
So
stick
could you just
to
say
the
why it's got to be an even number? Why does
Sorry?
it have to be an even number?
I didn't
You
understand.
said 2k.
Yeah, so so in the previous one, 2k, so you have 2k particles at most on each side. And their k should be a half integer. And for the inclusion process, k is just be some positive number, but you can have.
But I mean, just in the usual simple exclusion process,
Yeah,
you have just exactly 1 or 0 on each side.
Yes. So for k is a half, you get the simple exclusion process.
K could be a half integer.
Yes. So it's a half integer here.
Ah.
And I think the reason that they took half integers here is that it comes from representation theory of SU2.
I didn't see the half. Sorry.
Okay, so basically I will stick to the symmetric inclusion process, but actually everything we do for the inclusion process, you can also do for the exclusion process. Okay, so we're going to look at duality, so self-duality. And it turns out that if you have a reversible measure, and that's given over here, then you always have a self-dual process. So you have a reversible measure if you have a measure or a weight function on the state space with this property over here. So you write L as, well, that's the generator, that's some kind of matrix.
Wolter?
Yes?
I suppose you're trying at times to point at something. We rarely see you. I don't know if you have your cursor or something or your pen.
I should just write it.
But maybe we don't see much. I feel when you say here, we see no indication. Just to let you know.
Yes, I will just point with I will just write down an arrow or something. Okay, so we write the generator as a matrix.
But you see, we don't see. Now we see. We saw you
here.
Underline. Yes. Okay.
I will just try to do that. So we write L as some kind of matrix, and then the matrix elements and the weight function should satisfy this condition over here. So then it's called a reversible measure. So actually, what happens here, if you in probability theory, they call this a reversible measure, and for me, I'm more on the analytic side. It just means that L is some self-adjoint operator on little L2 with a weight function. Okay. So if we have a reversible measure, then you actually, there are kind of, say, trivial duality functions, and they're given over here. So these are these, well, Kronecker deltas divided by the weight function. And so this is quite easy to prove. So let's try to do that. So if you act with L on this function D here, D on, let's say, X and, well, let's call it N. So let's act on the first variable. Well, then you can write it out as a matrix, right? So you just you sum over y of L, X, Y of, well, on D, Y, N. So this is a Kronecker delta. So actually, this is only non-zero if I is equal to N, of course. So then you get L, X, N over Wn. And now you use this this reversible measure property, so the one over here. And then this is the same as, I should be careful, this is Lnx over Wx. And then you can reverse all these steps. And what you basically get is L acting on the, oh, it's not Y, it's on the n variable, dx. And so here you always have a, if you have a reversible measure, then you have a self-duality function, but it's still not a very useful one. But it's one that you can
Is the connection bad?
I'm sorry?
Sorry, I'm not sure if it's only for me, but I missed almost 20 seconds. But I don't know if it's for everybody or just for me.
It was just for you, Marco.
Okay, sorry about that.
Okay, so of course, then we would like to show that, well, let's stick to the symmetric inclusion process. There we have a reversible measure, and it's just a product of negative binomial distributions. And what you see here, so this binomial distribution has an extra parameter p. So here's the p in this weight function, and the process itself does not depend on p. Okay, so what you get is you get an extra parameter, and of course you get duality functions corresponding to this reversible measure. Those are called the cheap duality functions because you basically get them for free. And there you have this extra parameter, and this parameter can be useful later on because you can play a bit around with this parameter. Okay, so the symmetric inclusion process is a self-dual process, and we have this, well, this cheap duality functions, but that's not the most useful one. So there are more duality functions. So here's another one. This is called the classical duality function. This also still looks, well, not too bad. And then, okay, I will say later on how to find this classical duality function from the cheap duality function. But then, well, Frank Redig and Cristian Giardinà, they really try to, well, make a whole framework of studying these processes using duality, and they came up with another duality function. That's the one over here.
Sorry, before you go ahead, I don't know if you said it, but are your xi's and yi's integers?
Ah, yes. So the xi's, I didn't say it actually, but these, so the xi's and the yi's, they are all in the state space, so they are all integers. So xi and yi, they're all just natural numbers. Okay. So in studying these duality functions, they came up with, well, this 2f1 function. And actually, this is a polynomial. So this is actually a polynomial in yi. So if you look at just one of these 2f1 functions, so here we have a whole product, of course, but if you take one of them, it's a polynomial of degree xi in yi, or the other way around. Doesn't really matter, of course, here. And well, if you're a bit familiar with these kind of functions, then you recognize these as Meixner polynomials. So this is actually a Meixner polynomial. So here, the duality function is a product of Meixner polynomials. Okay, so they first found this by basically doing the whole computation with the...
Sorry, is it a product or is it a sum over product?
No, it's a product of polynomials.
It's factorizable.
Yes, so yeah, so it's actually, so actually you see here product of capital N polynomials. So you have a, this is actually a polynomial in n variables.
Oh, I see.
Okay, so if you look at all these duality functions, you basically see that every duality function is of this form, right? So it's a product of, well, say a function d, let's call it small d, of x and xi and yi. So it's all, well, kind of, say, trivial product, and these these functions small d, these are sometimes called the one-side duality functions. And of course, it doesn't make sense to look at the process at only one side. But actually in computations, it's really useful to have this one-side duality function. You can actually work on just one variable, and that's enough. And afterwards, you can just take a product. Okay, so at some point they found these Meixner polynomials as duality functions, and that was basically just by doing the computation with the generators. So the generators basically some difference operator. So they did the explicit computation on the Meixner polynomials. So that's actually quite some work, and there should be better ways, of course, to do this. And well, I will try to explain some of that.
So just another silly question. Isn't P the probability of moving right or left?
No. No, so P is basically just a parameter here. So the probability of moving right and left. So let's go back to the generator.
No, you said it was symmetric, so it should be equal to 1/2. But that's why I asked what the meaning of P was.
No, P is just an extra parameter here. So the process itself does not depend on P. So actually the probability is related to the rates that we have over here. And the rate of going to say to the right is the same as the rate of going to the left.
Okay. So P doesn't have the meaning of, it doesn't have anything to do with the probability.
No, it doesn't have anything to do with the process, actually. It's just an extra parameter that you can introduce here. Okay, so these were the duality functions. So let's try to, well, explain how you can get these Meixner polynomials as duality functions. And that's using scalar products. So we just make a scalar product. So this was the reversible measure, the WP. And you can choose any P that you like there. And you still have a scalar product, of course, and you still have a reversible measure. And the first, well, result here is very simple. If you take the scalar product of two duality functions, you get again a duality function. So this is almost so easy that you, well, people should have known this, but we couldn't find it in the literature. So, but this can actually be used to find these Meixner polynomials. So because it's so simple, let's try to prove this. So if you act with the generator, so I'm writing it down for the symmetric inclusion process here, but of course over here it says symmetric inclusion process, but it's actually, it works for any process with a reversible measure here. So if you act on this function d, say in the x variable, that just means that you act on, well, in the x variable on d1. And let's say, well, of course, this inner product is some kind of sum. So let's say we sum over a z. So I don't put a dot here, but a z. And now you can use that d1 and d2 are duality functions. So acting with L on the first variable of d1 is the same as acting on the second variable with L. So this is actually L acting on the z variable, x and z. And now, well, because we have a reversible measure, L is actually a self-adjoint operator, so you can throw it to the other side here. So we get d1 of x and z, and then L acting on the z variable of d2. And now, of course, you do the same. d2 is also a duality function. So acting on the z variable with L is the same as acting on the y variable. So this is L acting on the y variable. d2, y, and z. Okay, so then we have, of course, L acting on the y variable of our function d of x and y. So in this way, having two duality functions, well, you can just take a scalar product and you get a new duality function. So if you would do this with the cheap duality function, so these Kronecker deltas basically, well, we take the inner product of two Kronecker deltas and we get another Kronecker delta. So if you take two cheap duality functions, the outcome is again a cheap duality function. So for the cheap duality function, this is not so interesting, but what we do is we can do this with the classical duality functions. So these were these other products, but not the, well, not the difficult ones. So the difficult ones were these hypergeometric functions. Okay, so we do this with the classical duality functions. So we take just d1 and d2, both a classical duality function. Well, then this is the scalar product. So what we have over here. And well, you just do the summation, and what you get is a 2f1 function, or actually just the product of 2f1 functions, of course. So there is a very easy way to obtain these Meixner polynomials as duality functions. So just from the construction that you get that these are duality functions. So you don't have to do a very large computation here. Okay, so this shows that there are duality functions, but then it would still be nice to understand why these are orthogonal duality functions. Okay, so that's the next thing we looked at. So here's the theorem. If we have, again, two duality functions, d1 and d2, and these are already orthogonal in some sense, so these are actually bi-orthogonal duality functions. So in two ways. So here, in the first, here we have d1 with an x, and then d2 with y in the second variable, say. So d1 with x in the first variable, and d2 with y in the second variable. And the second one, it's d2 with x in the first variable and d1 with y in the second variable. So these are actually two different kind of bi-orthogonality relations. So if you have this and you make new functions, so d and d tilde, just by taking these scalar products, so then we already know that we get duality functions. And these are actually then again bi-orthogonal duality functions. Okay, so I'm not going to prove this, but the proof is actually just writing out the sums and interchanging summations, and then you're basically done. So it's not hard, but it's still, I'm not going to write it out now. Okay, so if we have, say, simple d1 and d2 functions, then we can make more complicated duality functions also satisfy a bi-orthogonality relation. Okay, so, well, we want to do this with the classical duality functions. And then we need some kind of orthogonality or bi-orthogonality relation for this classical duality function. So recall that these are just, well, quite simple products. Well, functions defined as quite a simple product. And now we use that we can actually play a bit around with this parameter p that we have. So I'm taking minus p and minus q here, and actually the weight function depends on the p. So you can use here that you can play around with this parameter p to get this orthogonality. And this is, so in the theorem we needed two kinds of orthogonality, but then we had a d1 and d2, and now my d1 and d2 are basically the same function. So the two orthogonalities, or the two bi-orthogonalities, are, well, basically the same relation now. And well, now we get a function d and a d tilde. So we have a d and a d tilde. And well, we just saw that these are basically Meixner polynomials. So we get two different Meixner polynomials here, and then we get a kind of bi-orthogonality relation for these Meixner polynomials. So from the, well, orthogonality of this simpler classical duality functions. Okay, so I'm saying this is a bi-orthogonality relation. So if you're familiar with these Meixner polynomials, well, you know that they just satisfy some kind of orthogonality relation, and actually it's exactly that relation, because what you get is here you get some Meixner polynomials, say, or actually a product of Meixner polynomials, say in X, and here you get something very similar, but now there's some function in front of it, which may also depend on X, and you can glue that onto the weight function, and then you get the usual orthogonality. So this gives a bi-orthogonality relation, but it's not nothing special, basically. Okay, so this basically explains these, well, the orthogonality of these duality functions that you can write as Meixner polynomials. So this was all for the inclusion process. So for this exclusion process, you can do everything completely the same, and then you get Krawtchouk polynomials. So there the orthogonality is from Krawtchouk polynomials. And again, if you are familiar with these polynomials, you know that Krawtchouk polynomials and Meixner polynomials are basically the same functions as hypergeometric functions.
May I ask a question?
Sure.
The Krawtchouk and the Meixner polynomial are intimately connected to SU2 and SU11. Is this connection useful in the picture here?
Yes, of course. So that was, of course, the next step. So there are other ways to find these functions. So one of these other ways using symmetries, and these symmetries will come exactly from those Lie algebras, yes. So, okay, so here's a general statement, which is also, if you try to write it out, it's one line, I think. If you have a self-duality function and you have an operator that commutes with the generator L for this process, then if you act with X on your duality function D, then it's again a duality function. So this is, well, quite easy. I think you just write it out and use the commutation relation, and then you're there. So, well, if you have a statement like this, then you can, of course, try to find new duality functions from your old duality functions. And of course, the functions to start with should be the cheap duality function. These are these Kronecker delta functions, basically. Those are very simple. You get it for free if you have a reversible measure. So you can act with certain symmetries on this cheap duality functions, and that will give you new duality functions. Right, so we should find the right symmetries, basically. And, well, okay, these will come from a Lie algebra. So basically, this is just the Lie algebra SL2. So we have three basis elements, H, E, and F, and these are well, I think the standard commutation relations. And it's the Lie algebra SU11 because we impose this star structure here where E star is minus F and F star is minus E, and H is a self-adjoint, basically. So this is SU11, so this will correspond to the symmetric inclusion process. And you can also do it for SU2. And this would be the symmetric exclusion process. And the thing that changes is that now E star will be F instead of minus F, and then F star will be E. So you just get rid of the minus sign. Okay, so what's the relation to the process then? Well, okay, we have this Casimir element. That's not in the Lie algebra itself, but in the universal enveloping algebra. And the nice thing about the Casimir element is that it commutes with every element in the Lie algebra. So it's actually in the center, and it's self-adjoint. So we have these two things here. It commutes with everything in the Lie algebra, and actually also everything in the enveloping algebra. And it's a self-adjoint element. And actually this Casimir will be closely related to the generator of the process. Okay, so what we need is a representation of our Lie algebra. So we represent the Lie algebra on an L2 space, on a Hilbert space. And we take the L2 space L2 of the natural numbers with this weight function here. So this was the reversible measure, or actually one of the components of the reversible measure. Okay, so, well, what do we do? Well, H sends f of x to f of x with some factor in front of it. E sends f of x to f of x minus 1. And F sends f of x to f of x plus 1. So these are, well, shift operators, if you like. And so if you're a bit familiar with representation theory of SU11, you recognize this as one of, as the principle, or no, not the principle, the discrete series representation of.
Wolter.
Yes.
What about parameter p? Because I see that in this representation, parameter p doesn't play any role. Yes.
No. So
yeah.
Exactly. So the p. Well, all the representations, they are usually labeled by just a k. Here we just have this extra p, so that well, if we act on L2 of n with this measure WKP, we have this extra parameter p, and we have this, well, the p ends up in the action of the Lie algebra to get exactly the star structure that we have here.
Okay.
So you can certainly you can make a unitary operator from say L2 with WKP to L2 WKQ, and these are all equivalent. Okay. So we have a representation in terms of difference operators. And then we need something, well, if we want to represent the Lie algebra on the tensor product of the two Hilbert space, we need the coproduct. And the coproduct for a Lie algebra is very simple. So it's like this here. So you act with x, say, on the second factor of your tensor product, and then you act with x on the first factor. So it's really easy here. So this is just for Lie algebra elements, and the Casimir itself is not in the Lie algebra, but then you extend this this coproduct as a Lie algebra or as a, not as a Lie algebra, as an algebra homomorphism to the universe enveloping algebra, and then you get, well, this expression for the Casimir. Okay, and this is actually this will be the generator of the process. So the symmetric inclusion process, this was the generator. So we've seen this before. And well, you see that basically the generator is just the sum of, well, difference operators acting on just two sides. So that will be the coproduct here. So I define here this operator y as basically the coproduct of the Casimir. And the Casimir itself on just one of the Hilbert spaces acts just as a constant times the identity. So these are just diagonal terms here. So they're not really important. And then you can just check that if you take y, and then I should explain the notation here. So this subscript y and j means that you act with the first factor of y on the ith factor of your tensor product, and the j, the second factor, acts in the jth factor. And there's a constant here which is not so important, and you can just check that this is actually the generator of your process. So actually the only, say, non-diagonal terms are the two terms over here in the Casimir. So these two terms, so f tensor e, that one corresponds to this term here, and the e tensor f corresponds to the term over here. So I don't know, did I explain this notation before? I think I forgot it, so maybe it's good to say what this means. xj, xji, so x is, of course, this is x1, so this is a vector x1 up to xn, and the ji means just that you subtract one in the xj variable, you add one in the xi variable. Okay, so actually the generator of your process is basically, so that's the important part here, that's basically the co-product of the Casimir. So if you want to study these processes using the Casimir, you only have to study two sides basically. And the nice thing is, well, now we want to find symmetries, and the Casimir commutes with everything in the Lie algebra. So actually every Lie algebra, or actually the co-product of a Lie algebra element, will be a symmetry for the co-product of the Casimir, so for the generator of the process. And because the co-product of a Lie algebra element acts in this simple way, it basically you only have to look at one side. So the co-product, of course, acts on two sides, but for the symmetries, we only have to consider one side because your co-product is such a simple thing, basically. Okay, so as I said, we only have to basically consider action of Lie algebra elements on the one side, so on one side duality functions. Okay, so, well, here are certain properties that we can use then. Namely, if we have a Lie algebra element, so, well, later on we will do this with E or F, and you, well, take x to the n here, or so E or F to the n, you act on a one-side duality function, then what you get is again a one-side duality function. Okay, and well, if you can do that for any x to the n, you can take power series. So we can act with the exponential function of E here, and there's an extra parameter alpha that you can specify, and I don't want to be, well, very precise here. So we just take the exponential function of alpha times E, and then we act on the one-side duality function, and you get again a one-side duality function. So it turns out, if you do that on the cheap duality function, so this is just the Kronecker delta function basically, you get exactly this classical duality function. Okay, and another thing that will be useful is that if you act with E on the cheap duality function on the first variable, so that's what we do here, that's the same as acting with F on the cheap duality function in the second variable. So the cheap duality function basically intertwines E and F. Okay. And then, well, now we can find a symmetry to go from the cheap duality function to these orthogonal duality functions. And the symmetry is actually acting with the exponential function of F and with the exponential function of E. And there are these coefficients alpha and beta here that you have to specify. And it turns out that this is actually a unitary symmetry. But okay, so let me explain how you can find this symmetry, because we already have the scalar product method. And actually the scalar product method is very useful to find these symmetries here. So we had the following, that the orthogonal duality function, so in x and n, that was actually so the scalar product of two classical duality functions. And I just gave this property that the classical duality function is, well, you can act with the symmetry on the cheap duality function to get the classical duality function. So if you act with the exponential of E on the cheap duality function, so instead of doing it for the whole duality function, we can actually do it for a one-side duality function, and that's of course much easier in the computation. So x, well, let's put a y here or something. And so this is the cheap duality function. And so acting with E, with the exponential of E on this gives the classical duality function, and we should do the same here. Well, let's do it with another one. this should be an n. So it should be something like this. And now you can play around a bit with this exponential functions, and then you actually get this s that's in the statement over here. So what you do is you can, well, basically take this one. So the the exponential of e, you can take it outside. So actually this acts on the x, right? And this one acts on the n. So let's put an n there. So you can take this one outside. And for this one, you use this intertwining property. So acting on the first variable with e is the same as acting on the second variable with f. So this is actually e of beta of f acting on the y here. Okay, so, well, now you can take the adjoint here. So you throw this operator to the other side. So the first one is just outside of your scalar product now. And, well, you take the adjoint. Well, the adjoint of f is minus e. So you get beta minus e, acting on the y variable now, of course. Okay, and now you use the intertwining property here again, and then you act with e beta of f. I think with a minus sign on the x variable now, dxy. Okay, so now it acts on the x variable, and you can take it outside again, and you get e to the alpha e and e to the minus beta f. And so I'm missing a minus sign here actually. So, well, it should be a minus sign. And then you take the inner product of the two classical duality, or the two cheap duality functions. And that's, of course, well, the inner product of two Kronecker deltas is again a Kronecker delta. So this is again the cheap duality function. So here you have your symmetry to get from the cheap duality functions to the orthogonal duality functions. So actually, I didn't say anything about the alpha and beta. You can choose them in terms of the p parameter that we have. And well, if you choose the right parameters, it's actually not hard to see that this is a unitary symmetry. And then, of course, you can use the unitarity to, well, to find the orthogonality relations, because if we take the inner product or the scalar product of two cheap duality functions, we get again a cheap duality function which is a Kronecker delta. And because of the unitarity, then the scalar product of the functions over here should also give you the Kronecker delta. So there's the orthogonality coming from the symmetries. Okay, so well, we have the scalar products, and actually with the scalar product we can also find symmetries. And of course there are other ways to find the symmetries, but it's actually closely related to the scalar product method. Okay, again, you can do the same in SU2. So this was in SU11. And you can do the same in SU2. And then you find the Krawtchouk polynomials again, and of course the orthogonality for the Krawtchouk polynomials. Okay, so those are the two methods, and we actually studied these for the symmetric processes. And then, well, this is, say, recent work. We also try to do that for the asymmetric processes. So I will only talk about the asymmetric exclusion process here. So this is actually called the generalized asymmetric exclusion process. So the usual ASEP is this one with k is a half. That means that you can have only one particle on each side. So you have either 1 or 0 particles on each side. So this is a generalization of that, because now you can have, say, again, 2k particles on each side. But the difference now is, so here's the generator. The difference with the previous one is that, well, particles can only move to neighboring sides. So you can move from I to I plus 1 or I minus 1, but not further than that, only to neighboring sites. And now moving to the left is not the same. So the rate of particles moving to the left is not the same as the rate of particles moving to the right. And you can see that here, because here we have the rates. These, so the first one, so the second one is basically the same as the first one, but we replace Q by minus Q, Q by Q inverse. So Q is some number, some positive number, so let's say between 0 and 1, and then of course Q inverse is larger than 1. So now you have, that's the asymmetric part here. And well, what you can do is try to do the same things, only, well, things will be a bit more complicated now. So you can, well, let's move to the other one. We can try to do this scalar product method again. So, well, there is again a reversible measure. So now the reversible measure is here with this. So here we have Q binomial functions. So if you have never seen these, they're kind of generalization of the usual binomials. And again, we have some parameters. So we had this extra parameter P in the previous one here. Well, we have something, you write it with an alpha here. So we have a reversible measure. And then, of course, we also have a cheap duality function. So this is definitely a self-dual process again. So we have a cheap duality function. And then, well, there is a way to find the classical duality functions. So actually, this generalized asymmetric exclusion process, this was introduced by Gioia Carinci and Cristian Giardinà and Frank Redig, and then Sasamoto also. So the four of them introduced this, and they already acted with symmetries basically on this cheap duality function, and then they found actually two kinds of classical duality functions. So these are the, say, the Q analogs of the classical duality function that we had before. So if you let Q tend to 1, then of course you get back to the symmetric process that we had before. But now if you look at these duality functions, these are no longer, so we still have kind of one-side duality functions, but they depend on this quantity over here. So the n minus I minus 1 is basically, that counts up all the particles to the left of side I. So these duality functions, they not only depend on the particle on the ith side, but also on all the particles on the left. So we still have kind of one-side duality functions, but they're not as simple anymore as in the symmetric case. But you can, so, okay, in this case, you cannot really work with the one-side duality functions, but the whole method of the, so this whole scalar product method still works. And then, well, you can do that. And then we find these, well, again, these kind of orthogonal polynomials as, so products of orthogonal polynomials as duality functions here. And, well, these are, well, Q analogs of Krawtchouk polynomials. So if you're familiar with these kind of polynomials, these are actually called the quantum Q Krawtchouk polynomials. Quantum Q.
So could you say, what is the relation between Q and the asymmetry?
Yeah, so basically okay, so let's go back to the generator here. So here we have the rate. So here, this is the rate. So the first one, let's pick another color. So this one. This is the rate for the particles moving to the right, basically. And the other one, this one, is the rate for particles moving to the left. And you see that the Q, so I cannot see from this expression which one is larger, but basically, well, we can take, for instance, K is a half. then this will actually, if we take k as a half, so then you are really in the hardcore exclusion case, then this is just, let's see, this is Q inverse, and this one will be just Q. So if Q is a number less than 1, it means that it's more likely for particles to go, let's see, from left to right than from right to left. So there's the asymmetry. So the Q basically gives you the asymmetry of this process.
So the Q is a real number?
It's a, yeah, so the Q is a real number. I see that I didn't write it down. So I think of Q as a number between 0 and 1, but you may also take it larger than 1.
But you just said it was negative a moment ago.
Ah, did I say that?
I thought you said that it was something.
That was a mistake then. Q is not Q is not a negative number. It's a positive number.
Between 0 and 1.
Let's say between 0 and 1. Okay. And if you let Q go to 1, then you are back to the symmetric case, basically.
So is there a simple, I mean, for the k equals a half, is there a simple relationship between Q and the probability of going right?
So the probability, I'm not completely sure. The probability of going right should then be e to the so the probabilities are the exponentials of the rate. So it should be the probability of going right. That's this one here. I think it should be e to the q then. Let's see if that's possible. No. That cannot be possible.
Well, you want it between 0 and 1.
So that's, I think I'm missing a minus sign here. Yeah, that should be a minus sign. So
But those probabilities are not homogeneous, right? They vary from site to site. Am I right?
No, they don't vary. They depend on the number of particles on the side. That's right. But in the hardcore exclusion process, so k is a half, you can actually, it doesn't depend on the number of particles anymore because there's only 1 particle or 0 particles.
Okay. Okay.
And in that case, it's just Q and Q inverse, basically.
Yeah.
And of course, well.
But John, to your question, the probabilities are circled in red. This is what they are.
Yeah, but I don't see. I mean, okay, it depends on I on k.
Yeah, but you're asking if you go to k.
Yeah. I'm just going to the classical case where k is a half.
Yeah. Well, then it's bound, I think, to be q on one side and 1 minus q the other.
Well, he just said it was something different, but okay, there is a formula.
Yeah. I don't think it's important at this point because we're going tight on time, Wolter. I would encourage you.
Yeah, I will finish it up. Okay, so we have this scalar product method. So we get this kind of products of quantum cube Krawtchouk polynomials here as duality functions. So here we have these products, but these are actually kind of non-trivial products because it depends on a parameter p here, and I wrote it out. So the p here depends on, say, particles. So if you're on the ith side, so the ith factor here, basically, it depends on the number of particles on the left and the number of dual particles on the right. So this is actually some kind of, say, Tratnik type Q orthogonal polynomial. And well, again, we can find the orthogonality relations in exactly the same way as we did before, but now we cannot use this one-side duality function, so we have to do it all at once. So it's a bit more complicated. And actually, well, we have this reversible measure here. This is not the reversible measure that we started with, but actually, well, you need to adjust it a bit. And well, you adjust the reversible measure by a function fx, but that only depends on the total number of particles. So for the process itself, that's a constant. Okay, so that's basically the result that you get for the orthogonal dualities in the asymmetric process. And well, I think it's about time to stop. So there you can do something with symmetries, and then you have to go to the so not to the Lie algebra, but actually to the quantum algebra, UQ of SU11 or SU2. So here I talked about the asymmetric exclusion process, and they also define something that's the generalized, well, asymmetric inclusion process. And well, you can basically do things very similar, and you get Q Meixner polynomials here. Okay, so I think this is a good point to stop here. So thank you
very much. Are there some questions? Anyone with questions? Sorry.
Yeah, could I ask a question, Luc?
Please, coming from afar.
Yes, going from one meeting to another.
Good to see you.
I was wondering, actually, Wolter, if it's kind of possible to classify what kind of orthogonal polynomials will actually appear in this kind of self-duality functions. Is it clear that you can get part of the ASCII scheme, or can you get all of them, or only the discrete ones, or is there some classification possible?
I'm not completely sure if
I had the same question, so I may just add to it. You get only Lie or quantum algebra related polynomials. Can you get, say, the Raka polynomials in the scheme?
I think so. In the classical, so for the symmetric systems, I don't think you can get any further than Meixner, and I can get to. I mean, you can also find dualities between different processes. There you can get to Laguerre, and I think Meixner and Laguerre, that's the highest that you get in the classical ASCII scheme. In the Q ASCII scheme, so we didn't work that out yet. But you can also go to, so these are all self-duality functions, but you can also, I think at least, do duality functions. And I think you can get up to Q Raka, because you can get Q Raka as matrix elements for just quantum SU2. So that's, I think you can get them as duality functions. So there should be some process related to these Q Raka polynomials.
So that would mean that by taking limits Q to 1 and other limits, you should be able to get all the discrete polynomials in the ASCII scheme and the Q ASCII scheme.
Yeah, my guess is that you can, yes. But I don't know what if Q tends to 1, if that still corresponds to, say, a symmetric limit, because here in this asymmetric, in this symmetric inclusion and exclusion process, there you cannot go higher up than Meixner. So maybe if you take limits, you get kind of different process, but I think there will still be an asymmetry there.
And in the quantum case, is your process operator also written as a sum of local operators, or not, because of the...
Yes, it is. So let's, here's the process generator. So here you see...
No, but I meant in terms of quantum algebra generators.
Yeah, it's basically still the co-product of the Casimir.
Okay. Anyone else with a question?
I have a small question. So for these multi-particle symmetric inclusion or exclusion, are these determinantal processes, like in the Kekel-half case?
I don't think so, no. I must say I'm not really an expert on these processes. but no, as far as I know, they're not the determinamental, I can't even pronounce it, processes.
Anyone else? Quick question. It's late, so short answers. If you have boundaries, the process you've described are closed, right? You don't have open. Anything describable if you open the boundaries? Well, I could just put all my questions. So you mentioned Sassamoto. He's described this process with boundary. He has the Askey-Wilson polynomials with a quite different setup using the matrix ansatz, any connection. So all these things that you see relations.
Okay, so what's the question?
Well, the question, okay, what can you do with, can you treat open boundaries? And
I'm not sure if you can do, so you can definitely, this generalized asymmetric exclusion process, they also defined it with open boundaries. Basically by doing this and saying we take a limit. So you can still define it. I think you can still, because if you, well, the number of particles is conserved, so you can basically define it and say, well, it should be 0 if you're far enough, basically. If you're side very far, there are no particles there. I think you can still define the duality functions, so the cheap duality functions and these classical duality functions. I'm quite sure that you can still define those because you just take these products. I'm not sure if you can do that with the orthogonal duality function, because then you would get kind of infinite products of Krawtchouk polynomials. I'm not sure how to treat those if there's any convergence there. But the processes itself, you can definitely define them with open boundaries.
All right. Well, your talk raised many interesting questions, but I'll save that for some other time. It's been a long day, especially for you. Anyone else with a pressing question? If not, Wolter, I will invite people to, maybe you can stop sharing and I'll invite people to open their cameras and to say a big thank you. We've much appreciated your talk. Thanks for joining us and enjoy your night. So, well
Thank you very much.
This is the last session, right?
This is closing our indeed our series for the semester. So to the regulars, if in case there's not another occasion, it's time to say Merry Christmas and may we have a better 2021.
So, we will take much.
Thank you very much.
Yes. So William, when do we resume? We resume at early January?
Yes,
William, are you there?
William might have disappeared. He might have disappeared because he has a young one. I don't know, but stay tuned.
Okay, I guess we'll just stay tuned for news. Okay,
that's
so
right.
everybody, if we don't meet again before Christmas, have a very Merry Christmas.
Merry Christmas to you. Bye.